All right. So the topic that
And
we, oh, go ahead. Who is it?
it's Emma. Will you be posting this
Mm-hmm. Sure.
on
Yes.
the same place as the rest of the lectures?
Yes.
Okay.
Okay. So this topic is called the mole and molar mass, and um, you kind of get used to it. You know, for some it clicks initially, like it makes sense, and for some it takes some time, but you eventually get used to it by the end of this term and get really good at this topic. It kind of becomes like second nature to you. So some chemistry terms, and remember that we are dealing with subatomic particles with masses of tiny, like 1.6 times 10 to the power of negative 24 grams, which are so tiny. So that's why some of the numbers you see here are really huge. Okay, so because there is a challenge of calculating the masses of subatomic particles because they were so tiny, we have to come up with the new terms to be able to easily calculate on the benchtop. Like, if you think of any scale on the benchtop, even in the labs, that, goes up to, maybe a 1/100th of a gram, or maybe 1/1000th of a gram. But beyond that, you cannot actually, measure with the normal scales. You could easily measure in grams. So because it is so easy to measure it in grams, but not in really tiny quantities like the actual mass of the atoms, we come up with a word called a mole. So a mole in chemistry is defined as the amount of a substance, like number of particles, substance here means, that contains as many elementary entities as there are atoms in exactly carbon 12. So carbon 12, if you have 12 grams of carbon 12, and if you try to identify how many of carbon atoms present in that carbon 12, that many atoms are defined as mole. So that number is happened to be 6.021 times 10 to the power of 23. So in a 12 grams of carbon 12 sample, there happen to be these many individual carbon atoms. So we are taking it as a basis because it is kind of standard, like, for kilogram or pound or what are other units. I think these two are good enough. For kilogram, how there is a defined mass, just like standard we take, just like that we are taking for mole this number as a standard, and this number is your best friend now, and you could call him whenever you want to call him. It is proposed by Avogadro, and this number is popular as Avogadro's number. So I'm just going to show you how to relate and how to make sense of this number. Is one way we always tell is how you use mole to communicate. Is like, you don't say I'm going to buy 12x, or I'm going to need 6x, or I'm going to need 24x. You kind of say it in dozen because that's kind of popular way to say it, and it is very easy to communicate because when you say dozen, people know that you meant 12. Just like that in chemistry, when you say mole, people know that you meant to say 6.02 times 10 to the power of 23 particles. All right. Any questions now before I jump on to next slide? Do you guys want me to repeat anything? Okay, here nothing. Let me move forward. So I just said it briefly in the previous slide, and I'm just reminding you the actual mass of protons and neutrons and electrons, and why it is, challenged to measure the individual atoms, because they have so tiny mass in grams. See, they were about 10 to the power of negative 24. So there is virtually no way for us to measure individual atoms are protons or neutrons. So because it is impossible to measure, these measurements are too small, we have to come up with a new term, which is what a mole is. So mole by definition, again, I'm going to repeat this because it takes some time for some until it clicks it. So if you have 12 grams of carbon-12 sample, that 12 grams of carbon-12 sample, when it is identified how many number of carbon-12 atoms in it, it is found that there are 6.022 times 10 to the power of 23 atoms. That number, because it is identified by Avogadro, so we are calling that number as Avogadro's number, okay? So because it is a equality now, 1 mole is equal to 6.022 times 10 to the power of 22. You can use that in the conversion factors to convert one unit into another, because you have a standard definition now, what is 1 mole should contain. So if you were asked to identify how many number of atoms a 2 mole sample contains, you could calculate it using this one as a equality. Which is what you kind of did it in chapter 1 when you do the dimensional analysis conversion factors. You basically chose a known equality and made a conversion factor and you converted it. So which is what we are going to practice now. So the question is simply asking how many molecules are contained in 5 moles of carbon dioxide. So here, I don't want you to get distracted. Does it really matter if it is carbon dioxide or just carbon or water? If it is asking you to identify how many molecules contained in 5 moles. I would like to hear anyone say something.
It does,
Does
right?
it really matter? Bradley, say it.
It does not matter because Avogadro's number isn't unit-based, right?
Exactly. Avogadro number talks about how many particles are present in it. It doesn't care about what particle it is. Like, if you say 1 dozen eggs, you're not really cared about if the egg looks in white in color or brown in color or the Easter eggs. You're just saying eggs. Just like that, molecule doesn't matter here. So don't get distracted by what molecule it is. I want you to laser focus on what the problem is asking. Problem is asking how many molecules are present in 5 moles. Whatever the name followed by it, do not get distracted. I have seen over the years students distracting with whatever the sample it is given and going in wrong ways, okay? So now, because you already know the equality between mole and a particle, we are going to use it to set up the equation. And this is kind of information I already gave you in chapter 1, and you will see some of the similar stuff, how to set up the equations. And in this case, it is what you actually required to do throughout this year in any chemistry class. It's going to be now your kind of bread and butter. Like I said, all of you will eventually get better at it because we use this in almost every chapter from chapter 8. You have to do this. It's kind of your second nature. So now to do this problem, first, let's identify what is given to you. 5 moles of a sample is given to you. And what the question is asking you to do. The question is asking you to identify how many molecules are there, okay? So now think about what is the equality between required moles, required molecules, and given moles. There is a direct relationship. So think about this. Now remember we discussed this in chapter 1, where you set up the conversion factor to have the given unit in the denominator so that you could cancel those unwanted units. You end up with the required answer. Now, based on that, if you want, you can start setting up the equation right now. So we are taking the Avogadro's relationship, 1 mole is equal to those many molecules. And you can write 2 conversion factors from any equality relationship. So you are setting up 2 conversion factors. Now imagine what is the given unit to you and pick the right conversion factor that you need to pick. Tell me which conversion factor should I pick to get my answer in molecules. Jared, you're muted.
Yeah.
Can anyone give me a guess on which
It's
conversion
the
factor you
second
should be choosing?
Is it 6.02?
The one on the right.
Yeah.
One on the right. Why? One on the right.
Because the one on the left would give you a number ridiculously small, like even too small for chemistry, right?
Let me think about it. 5 over, well, yeah, I would say. And good observation, but the right word to say it is, it doesn't help our cause in canceling the units. Always pay attention to the units. You want to remove the moles in your units and end up with the unit molecules. So if you choose this one, the right side one, like one of you guys said, maybe Cameron or others also, you multiply this one with 5 moles. So this one will help you cancel the unit. Let me show you how. This is your given unit, 5 moles. You are choosing this conversion factor so that you could cancel these moles and moles, that you would end up with the molecules as your answer, which is what we are looking for. So in 5 moles, there happen to be 3.0 times 10 to the power of 24 molecules. Okay, so whenever you do math, always get a feel for it. So if 1 mole contains 10 to the power of 23 molecules, for 5 moles, whatever the number you're trying to get should be looking a little bit bigger than this number, right? So just by getting 24, then you can say that, oh, I'm in right direction, right? Just for the eye test, it passed the eye test, right? It's 10 to the power of 24 now, not 23, which means you're in right direction. But if that number happened to be 10 to the power of 9, let's say, you need to recheck your calculations. You're doing something wrong. You set up the equation something wrong. Maybe you chose this equation instead of correct equation, because 5 moles should yield more amount of molecules than 1 mole, right? So always, give a eye test for your answer so that you would avoid, rookie mistakes, I would call, right? So what you know so far is how a mole is related to number of molecules. Thankfully, one guy already did it, so we don't have to find it by our own. You just need to convert it on paper, okay? Now also, because, excuse me, because we already know mass of each single atomic mass unit, right, in grams. I showed you that. Let me show you again what it is, because I want you to make the connection to the topic as soon as possible. You already know the mass of each subatomic particle, excuse me, of proton and neutron in grams. So because this is so tiny, and because you already know what is 1 mole is, a bunch of atoms in Avogadro's number, you are using it to define mass in some meaningful number. That is called molar mass, okay? A molar mass is a mass of a substance in grams of 1 mole of a substance. So this is where you need to have a clear mind. So you already know how many particles in 1 mole contains. Now we are trying to learn how much of a mass 1 mole of a substance contains. So 1 mole of any substance contains mass in grams, and that mass in grams differs if you have a different atom, if you have a different isotope, if you have a different molecule. Because what we learn is each atom will have different number of protons. Even same atom can have different isotopes, so it is going to vary. So it is going to be equal to the molar mass. So thankfully, in the periodic table, what you already see is average atomic mass. So that mass is directly equal to your molar mass. For example, for carbon, you will see that 1 mole will have 12, 1 mole of carbon molecule is going to weigh 12 grams, because that's what you would find it as average atomic mass unit. For oxygen, 1 mole of oxygen contains 6.02 times 10 to the power of atoms. Those many oxygen atoms is going to weigh 16 grams. 1 mole of oxygen atoms is going to weigh 16 grams. Similarly, 1 mole of hydrogen atoms is going to weigh 1 gram only, because that is the average atomic mass. Am I making sense? Okay. If not immediately, but it's going to be, click to you in just a couple of minutes. All right. So now
That mean that means just like molar mass is equal to the atomic mass.
the average atomic mass, yes.
Oh, okay then. Okay.
Average atomic mass. So again, I just have here, to help you imagine what the hell I'm talking about. Let's say you know that dozen eggs contains 12 eggs, and a dozen bananas contains 12 bananas, but do you expect them to weigh the same, dozen eggs? No, because they were different. Just like how eggs are different from bananas, one element is different from another element, right? You wouldn't exchange, let's say, 12 drumsticks with 12 French fries, right? Because it's not a fair trade. You would end up starving if you're the one that is getting 12 French fries instead of 12 drumsticks, right? Because they were just different molecules. They have different value. Just like that, atoms has a different value. That value we calculate in terms of atomic mass, in terms of how many protons it contains, and in terms of how many neutrons it contains, right? So that's why molar mass is different for each molecule, each element, and it is determined by how many atomic mass units it contains. And thankfully, we already got that information in the periodic table for each element, that we learn how to calculate the average atomic mass using the isotopic abundances, right? So what you are seeing here is a mole of different samples. So you're looking at 1 mole of helium gas in a balloon, but it only weighs like 4 grams. You're looking at 1 mole of water here that has 18 grams in it. And you're looking at 1 mole of copper that has like 63.5 grams in it. All of them are 1 mole samples. Even this sodium chloride is 1 mole. It's going to weigh, like, if I'm not mistaken, 53.5 or 54.5, something like that. And 1 mole of sugar is going to weigh like 180 grams. And I don't have the number of aluminum on top of my head. You can find it in periodic table. Somewhere close to 26, 27, like that. So what it says is that 1 mole of different molecule is going to weigh differently, and you could easily identify it based on the average atomic mass of the sample. Are we clear so far? Okay, all right, let's practice it. So the problem is asking how many moles are present in 0.5 grams of aspirin. And the aspirin molecular formula is given as C9H8O4. So before we start working on this, you need to know how to identify, you need to know how to identify molecular weight or molecular formula in atomic mass units. Do you know how to do that for a molecule? Do you guys remember we doing that?
I don't.
Okay, so how we do is for each element that is present, excuse me, I'm getting it, chat message. Let's see. All right, I'll record this and post it. So how do you do this is you will try to identify each individual atomic mass of each different element, and you multiply with how many number of times it is present. So in aspirin, there are 9 carbons. So each carbon we know that weighs 12.01 atomic mass units. So you weigh those 12.01 with 9 times. And we know hydrogen is going to weigh 1.008 atomic mass units. You multiply with 8. And you know that oxygen is going to weigh 16 atomic mass units, and you multiply with 4. So you combine all of those numbers, to get the atomic mass unit of an aspirin in atomic mass units. And once you get that, okay, you say what is the molar mass in grams, which is same magnitude of atomic mass units, but one molecule is going to weigh, let me give you a number. Anyone calculated? 9 carbon times 12.01, 8 hydrogens times 1.008, 4 oxygens times 16. What is the total atomic mass unit of aspirin? Anyone had the number? You guys are too slow. Ahmad, where are you?
I'm still here. I'm calculating it. Give me a second.
Yeah, I think I got 180.154.
Sounds about right. Sounds about right. That is how you would calculate the molecular formula. So now you got the molecular formula in atomic mass units because it is the molecular formula of one molecule. But if you have 1 mole of them, it's going to weigh 180.02 grams, because we know how we define the 1 mole, how many molecules it contains, and we converted it back to the molar mass in grams, which happen to be the same as molecular formula in grams. Now, let's see what we do. So you were given half a gram and you were asked to identify how many moles are present. So given information is 0.5 grams of aspirin. Required information is moles of aspirin. So the same pattern. You are going to multiply your given unit with a conversion factor that facilitates the conversion of given unit into required unit. Thankfully here, it is only one-step calculation because we happen to know that 1 mole of aspirin is going to weigh 180.02 grams. Let me read my chat message again. All right, safe drive, good luck. Excuse me. All right, let me go to next slide. So this is the plan. So you can set up the equation now if you know how to do it, but I'm just going to walk you through slowly. So now this is going to be our equality that we are going to use. And that equality is always changes because in this case it is aspirin, in some other case it may be water, or it may be a copper, or it may be a sugar, right? So this number always going to change based on what you have here as the molecular formula. So you can write 2 conversion factors with it, and you always need to choose the right one to facilitate the unit conversions. Which one of the shown conversion factors is the correct one for you to use, and why? Ahmad, go.
I think the first one, the left one, would be the right one. That's what I think. I'm not positive here.
Okay, all right. So the given unit is what?
Oh, sorry. It's the right one. It's the right one.
It's the right one because the given unit is grams.
Yeah.
So you should have the given unit in grams in the denominator.
Sorry.
Right? So let's choose that one and set up the equation. 0.5 grams multiplied with this conversion factor. Cancel the grams. End up with the answer that it should have 2 significant figures because in the given unit you have 2 significant figures. So this should be our answer. So are you guys following me so far? Okay, this is what you have to do a lot in general chemistry. Okay. Everything that we discussed leads here. of course, this book has different set of problems, but I created this to give one complete picture so that you will have the compartmentalization and you will have something easy to compare one with another and avoid confusion between one process and another process. So I think this is the best plan for us to work on. So we are going to work on this, and if you start answering these already, you are advanced. Again, even if you didn't get it right here already, it is fine. You have lots of time to work on this one. All right, so we are going to fill the empty number or amounts of any one of the columns using just one information. Okay, so let's start with the 281 grams of iron. If you know there are 281 grams of iron, can you identify how many number of moles present in it and how many number of atoms or molecules present in it? Actually, you can, because we already know how a mole is related to molar mass of any molecule or atom in grams. So you could use that as a conversion factor and convert. And we already learned that a mole and amount of particles is related based on Avogadro's number. So we can use that. So what do you think it should go here? Anyone? I have all the time. I will wait until you guys work on it. So there should be a conversion factor. Give me that conversion factor. Did you raise your hand, Bradley?
Yes, sorry.
I can only see your head because you are too close to camera. I'm not complaining.
So
that's your hand.
yes, that was just old instincts kicking in, I guess. The conversion factor would be 1 mole over 55.845 grams, right? Because it's
fantastic. What is your thought process of coming to that?
Well, we know that the atomic mass number is like that number in grams is equal to 1 mole of that element, and so if we know the element, so we know its atomic mass number, so we're able to do the conversion that way.
Yeah. Where did you get that number? Which number you said? 58? Did you say?
55.845. I just have a periodic table right here.
That's where he got it from. So because it is iron and it is very simple, he plugged it right out of the periodic table. Oh, there is some chaos going on in my house right now with the twins. So that's the conversion factor. If you cancel it, you will have a 5 moles of iron. Right? Now, can we convert these 5 moles of iron to amount of atoms in this case? If so, how can we do that?
It's multiplied by 6.022 plus 10 over, I don't know how to say 23.
If you multiply with 6.022, do you think you can cancel the I think you're right. Yes. Yes. Actually, I'm distracted with what I'm hearing. Yes, you are correct. Can you say it again? I'm going to see what's going on. Just give me a second. No, there's kids being kids. They're just learning how to cry and make us mad. All right. So as Monica said, if we multiply that with the conversion factor of Avogadro's number with the molecules on the top and mole on the bottom, you can cancel the moles and end up with, anyone calculated? Ahmad, you are my trump card.
Hold on. I'm still calculating it. Hold on. I'm with you. Hold on a second.
Okay. Others can beat him too if you have calculator.
Okay, I got it. It's 3.0 e to the 24.
Perfect. That's what I got. So when you tried it with the calculator, this is the number you should end up with.
That was close.
Right? So let's focus on, if you start with moles, how do you go to amount of grams and how do you go to amount of molecules? Let's go left first. So if you want to convert 7 moles of iodine, how do you do that?
Is 1 mole over 126.904 of ion.
Okay, where did you get 126.4?
For the table, periodic table, it says the mass. Oh, well. Sorry.
You're fine. From the periodic table, I know where you get it, and I want to ask. So the number that you saw iodine in the periodic table, is it for one element or more than one element?
Yes, one. It says
Okay.
ion.
So what are we seeing here? Is it, am I asking for single element?
Oh, I forget that. Yeah.
That's what I call rookie mistake again. So there are actually 2 iodine atoms, not single iodine atoms. So you are going to have a different molar mass than single iodine. So what is the correct conversion factor?
Is it 1 mole over 252.8
Okay.
grams of iodine?
If you write 1 mole over 258.8, write it down, see if you can cancel the units or not. I think you said reverse. Actually, we should be having 253.8 grams over 1 mole.
Oh, that's what I wrote down. I just said it wrong.
Okay, okay. All right. So this is what it should be, so that you will have moles and moles cancel each other. So you end up with, what's the answer? Anyone?
Would it be 1,776.6 grams?
Okay. That number look really large. Do you need to refine that number to any number of significant figures, you think?
It can be reduced to 1780 grams.
1780 grams. That will be correct because
I just rounded up to the near 10th.
Yeah.
Yep.
You can only have maximum of 3 significant figures in 1870. You can call that one having 3 significant figures also, because you get to choose if you want to count the last 0 or not. So this time we say that we are not counting it. Still works. Or you can convert that number to scientific notation and say like 1.78 times 10 to the power of 3. It also works if you want to be precise. All right. Now let's fill up this column. So 7 moles of iodine. How many iodine molecules are present in 7 moles? What is going to be your conversion factor?
Oh, it's going to be the same as the last one. It's going to be just 6.02 times 10 to the 23rd over 1 mole.
Sounds about right. And how many molecules of iodine we are going to get?
Hold on, I haven't calculated that yet. Hold on. Okay, so I'm not sure, but I'm getting 4.2 e to the 24th. This is not sure.
Okay, 4.2. So do you have
So-
correct significant figures?
So it's 4.2, 4.2093 times 10 to the 24th. So let's just say 4.2 times 10 to the 24th.
Yeah, we cannot say 4.2 because you need to have 3 significant figures.
So can we say 4.21 then? Because 4.209.
Okay, you got some computation from Bradley here. He's saying 4.22 and you're saying 4.21.
Okay, hold on. What am I missing? What am I missing? Hold on a second.
Is Bradley missing something or are you missing something? Others can check the discussion.
I'm probably missing something. Yeah, hold on a second. Let me make the calculation again. Hold on.
I calculated right now and I got 4.21 times 10 to the 24th as well.
Okay, how do you get 4.21? Why 4.22 would be wrong?
So I realized what I did wrong. In my calculation, I did 6.022 instead of just 6.02 times 10 to the 23rd. So I had too much rounding.
Okay. It shouldn't have made that big a difference, but okay, if it made a difference, yeah, sure. All right. Oh, wait. Okay, good job. Let's fill up this one and you would know everything you need to know about this topic. So let's say you are only given the amount of molecules, and how do you identify moles and grams? You are given molecules only. You are asked to identify how many moles of sulfur present in 2.3 times 10 to the power of 23 molecules and how much it is going to weigh this sample. How do you do that?
You would have to start with Avogadro's number.
Fantastic, yes. Avogadro's number talks about amount of molecules in 1 mole. And how do you set up that?
The conversion factor we want is going to be 1 mole over 6.02 times 10 to the 23rd molecules, right?
Correct. There you go. If you do that, how many moles you got?
I have, I don't know if I'm right, 0.38.
Correct. I understand that you paid attention to significant figures and trying to give the answer. That's good. Actually, what you said, I don't want to point you wrong, but if your final answer is going to be only moles, yes, you can directly give the answer as 0.38. because it is part of the ongoing equations, you can also use the larger number because you don't want to round up in the middle because you are using that number to go further. There are both 3.8 and both 3.75 is also correct, depending on is it a final answer or is it still in the middle of the calculations. I put 0.375 because I'm considering this number as still in the middle of the calculation. So I don't want to set up a bad example. That's why I still had it, because you're going to use it to convert into grams. But your number also correct. So how do you convert 0.375 moles of sulfur into grams? You're muted, Bradley.
And my bad, mostly talking to myself.
Okay. Chris, how are you doing there? Chris, are you there? Taylor, are you there?
Yeah.
Okay. Do you have any opinion on how to solve the last missing part in this table?
Like what conversion you would use, or?
Yeah. Do you need any help?
No, I'm just trying to figure out the amount.
Okay. Do you want to think out loud? We are all curiously waiting what you're going to say. Or I can re-explain.
Wait, what?
Do you want to think out loud? I'm kind of waiting on you. But if you need time, I can just, explain it.
Could you just explain it?
Okay. So what we have here is a moles of a compound called sulfur. It has the molecular formula of S8, and we are trying to identify how many grams of S8 is present in 0.375 moles. Okay. So only clue that we have is how much of any matter is going to weigh if you have 1 mole of them. That is equal to its atomic mass units that you find in the periodic table, but in grams. So you can identify for single sulfur what is the atomic mass unit of it is, and using that, by multiplying with 8, you can identify the atomic mass unit of S8. So that should be, did anyone calculate it? Can you guys give me atomic mass?
Isn't it 200?
Yes, 256.3 atomic mass units if you have one single sulfur 8. But if you have 1 mole of them, so you have same number, but in grams as a unit. So you have 256.3 grams in 1 mole of sulfur 8. So to convert moles to grams, you would set up a conversion factor with grams in the numerator and moles in the denominator, so that you could cancel mole and mole and end up with the answer. Anyone has any number to throw me at?
96 grams.
96 grams sounds perfect, because the starting number you started with has two significant figures, so 96 grams. So in 96 grams, you have these many molecules. In 96 grams, you have these many moles. Or in these many moles, you have these many grams. So this table is everything that you need to know. You need to know how to comfortably convert grams to moles and moles to molecules, or atoms to moles, or moles to mass in grams. And I set up this table because I have seen students getting confused which equations to use, which conversion factors to use when they are trying to convert one unit into another. So that's why I want to combine everything into one, so that you have no way of confusing. Again, I understand if it takes time, it takes time. If it takes time, it takes time, but eventually you will get it. Okay. That's all I have, and everything remaining is included in our book. Basically, more problems that you can work on, that you could work on right away, by looking at this PowerPoint slide. But I don't have any new information other than what we just discussed, except a request from you and scientific community that do not throw away your plastic bottles, because you just learn how many atoms are present in 1 mole, like a quadrillion molecules in 1 mole, right, of any sample that you have. So if you happen to have 1 mole of plastic bottle, it's never going to go away. Even after degradation of 1,000 and 1,000 years, still there are going to be small molecules flying around. That's why, well, we already started seeing a microplastics. You would have heard the word microplastic. What it is these plastic bottles dissolved in sea or ocean or in ground, and they were joining our food system. If you find a fish nowadays, most likely you can find a tiny quantity of microplastic, because they were drinking the seawater, which is contaminated by these plastic pollutants. That's why we need to recycle, not throw stuff. Right. That's all I have. There are examples that you can practice from the book. These are all the book examples that you could practice in your free time, but we already discussed how to do all of this. And this is what book has, how to convert one unit into another. And I'm not a huge fan of it, but if you like it, you can follow it. I am fan of how I showed in the table, how I filled up. That is, I think, the best method to do it. But if you find it appealing to you, you're welcome to use it. All right. Let me answer any questions you may have on this topic now.